As we saw in the previous unit, hydrostatic pressure exerts forces on submerged objects. The hydrostatic pressure P equals the density ρ times the acceleration of gravity g times the depth h underwater. Pressure increases with increasing depth. Therefore, the force exerted by pressure on an area on the lower part of a submerged object is greater than the force exerted on an area of the same size on the upper part of the object. Because the forces are greater on the lower part of the object, there is a net force on the object. Next, we'll compute the net force on a more simply shaped object. But first, let's briefly review what we know about forces acting on submerged objects. This box is upright in the water, and its top surface is 1.5 meters under the surface. Its top is square and measures 0.80 meters on a side. What is the magnitude and direction of the pressure force exerted on the top of the box?
Try again. Try again. Correct.
What is the net force on the box from hydrostatic pressure? The force due to pressure on the top of the box, F sub t, points down. Its magnitude is the pressure, rho g h sub t, times the area of the top A, where h sub t is the depth of the top. The force on the bottom of the box, F sub b, is directed upward, and its magnitude is proportional to the depth of the bottom of the box, h sub b. There are also pressure forces on the sides of the box, but the forces on the opposite sides of the box cancel. Now let's determine the net force on the box due to hydrostatic pressure. The forces on the sides of the box cancel, and the forces on the top and bottom are directed vertically. Defining upward as positive, we obtain the net force as shown. The net force is directed upward. This upward force is the buoyancy force. Let's see how the buoyancy force affects the apparent weight of this container, which is filled with sand. The weight of the container of sand stretches the spring on the scale. When we weigh the same container underwater, its apparent weight is less, as you can see from the scale. What is the magnitude of the buoyancy force? Notice that the difference in height between the top and the bottom of the box times its cross-sectional area A is its volume V. The density of water ρ times the volume of water V is equal to the mass of the water displaced by the box m sub W. The buoyancy force is equal to the mass of the water displaced times the acceleration of gravity. This is the weight of the water. The buoyancy force is equal in magnitude to the weight of the water displaced. This is Archimedes' Principle. Although we derived it for a simple shape, it holds for objects of any shape. The buoyancy force on a body is directed upward, opposite to gravity. What is the weight of a balloon full of water if the radius of the balloon is 0.15 meters?
Correct.
Now, what is the apparent weight of this balloon underwater?
Correct.
If a container of sand has a volume of half a liter, or 50 cubic centimeters, and a mass of 0.83 kilograms, what is its apparent weight in the air and underwater? The weight of the container W is equal to the mass m times the acceleration of gravity g. The weight is 8.2 newtons. According to Archimedes' Principle, the apparent weight of the container underwater should be decreased by the weight of the displaced water. That weight, W sub W, is the density of water, rho sub W, times the volume, V, times the acceleration of gravity, g. The weight of the container of sand underwater, W sub S, is then 3.3 newtons. What is the apparent weight of a block of aluminum 0.10 meters by 0.15 meters by 0.30 meters immersed in water? Use 2,700 kilograms per meter cubed for the density of aluminum. The top of the block is 2.0 meters below the surface.
Try again. Correct.
Let's see how the buoyancy force affects the apparent weight. This container is filled with water. The weight of the container of water stretches the spring on the scale. When we weigh the same container under water, its weight is nearly zero, as you can see from the scale. Archimedes' principle predicts that the weight of a submerged mass of water is exactly cancelled by the buoyancy force of the surrounding water. This block of wood floats on the water surface. Because the density of wood is less than that of water, if it is submerged, it weighs less than the water it displaces. The weight, mg, is less than the buoyancy force, F sub b. The wood has a negative apparent weight under water. When the block is released, it returns to the surface. On the surface, the block displaces just enough water for the buoyancy force to balance its weight. Archimedes' principle applies to partially submerged objects as well as fully submerged ones. In the case of a floating object, the weight of the object is equal to the weight of the displaced water. This block of wood is 0.10 meters thick by 0.20 meters by 0.40 meters. It has sunk evenly to a depth of 5.0 centimeters. What is the weight of the block?
Try again. Correct.
The block of wood must be pushed down to make it stay underwater. Is the buoyant force equal to the weight of the block in this case?
Correct.
The fraction of a floating object above the surface is related to its density. The weight of a floating object is equal to the weight of the water it displaces. W is the weight of the object, V sub W is the volume of water displaced, rho sub W is the density of water, and G is the acceleration of gravity. The weight of the floating object is also equal to its total volume V times its density, rho, times G. Equating these two expressions leads to the result that the fraction that is submerged is equal to its specific gravity. The specific gravity of ice is about 0.9. About 90% of the volume of an iceberg is underwater.